Chapter 9 focuses on proteins. So we're going to have a short conversation about the structure of proteins, and we'll talk a little bit about some of the roles protein play in the human body. So regardless of the form of protein that we might ingest, call it a vegetable source of protein, maybe it's dairy, it could be red meat, it could be fish, we have a digestive process. And what we essentially do is to break down these protein structures, which can be quite large and complex. We break them down into essentially what we call the building blocks, which are amino acids. Now, ultimately, that's what we put into the blood. We can move couplings of 2 and 3 amino acids kind of through our intestinal wall. And once in the intestinal wall, we further break them up into kind of their individual building blocks. And that's what we carry throughout the body. Now, these amino acids, we can differentiate them into what we call essential amino acids and non-essential amino acids. Now, first of all, when we talk about amino acids, they are an abundance of amino acids in nature. But there's only about 20 that we consider to be nutritionally important to the body. But the difference between an essential amino acid and a non-essential amino acid is fundamentally that we cannot manufacture essential amino acids. Therefore, we have to obtain them from our diet. By comparison, a non-essential amino acid is something that we can manufacture in our body. So we can take another non-essential amino acid and convert it to a different non-essential amino acid. But interestingly, within the category of non-essential amino acids, we have some that we call conditionally essential and some that we call dispensable. Now, the conditionally essential ones are those that we can certainly make, but sometimes we don't make them in adequate quantities. So this is where sometimes supplementation or a food source might benefit us. The dispensable amino acids are ones that we typically don't have any issues with. Now, how is it that we can simply convert one non-essential amino acid to another? Well, we just got to look at the structure. If we look at the structure of an amino acid, we generally see that they have kind of what we call a skeleton. So you can kind of see in the illustration there, we have this thing called a carboxyl group, we have an amino group, and that's pretty much standard on all amino acids. And then we have this thing called a side chain. And this is what actually differentiates all the different amino acids from each other. That side chain can be very simple, it can be very convoluted. Now, if we are converting one amino acid to another amino acid, all we've got to do is just reformulate the side chain. But we also know that we can use amino acids to make glucose. Certain amino acids are called glucogenic, which means they have the ability to generate glucose. Other ones are called ketogenic, which means we kind of produce substrates that can feed into the energy pathway. But there's a fundamental problem. When we look at the conversion of proteins to glucose, and in some cases proteins to fats, yes, it is true, excessive amount of proteins can also be converted to fats. We see that there's an element that becomes a problem for us. Now, carbohydrates and fats collectively are called hydrocarbons, implying that they have hydrogen, oxygen, and carbon. Well, if we look at the skeleton of the amino acid, we also notice that there's nitrogen. And nitrogen has no place in the energy pathways, nor does it have a place when we are manufacturing glucose or fatty acids. So what we have to do is to remove it. Well, this is a task that is primarily handled by the liver. And what we are doing is removing that amino group. So the process of removing that amino group is called deamination. So if we move that amino group, what we have remaining essentially is a skeleton. And with that skeleton, we can then either feed it into the energy pathways or manufacture a different macronutrient. But what becomes of the amino group? Well, left unchecked, it becomes a problem because that can form ammonia. And ammonia is somewhat toxic. So what we do, primarily again in the liver, is we convert it to a product called urea, which we then pass to the kidneys, and we can filter it through the kidneys and excrete it as part of our urine. Now we talk about this idea of storing macronutrients in the body. Now, we've already established that we can store carbohydrates, right, as glycogen. We can also store an abundance of fats. We have virtually a limitless capacity to store fats in our body in different locations. But what becomes of excess protein in our diet? Well, in a perfect world, we'd be eating just the right amount of protein to be able to do what? Utilize all those amino acids as building blocks to build muscle tissue. And sometimes we are deficient, and other times we are consuming protein in excess. But let's look at what happens when the body needs protein. Now remember, protein is just not used simply to build muscle mass. We have an assortment of different structures and compounds in the human body that rely on proteins. For example, hormones. Hormones like insulin, they're made from amino acids. So enzymes, hormones, and red blood cells and lots of other structures are derived from protein. So what we need to do is to have a reservoir of sorts that we can draw upon anytime we want to manufacture any of these compounds or structures. And so the question we are then faced with is, where do those amino acids come? Where do those building blocks come from? Well, we typically have three sources of amino acids. One is our dietary protein. We eat protein, or we're supposed to eat protein, on a daily basis to do what? To make sure that we're providing our body with adequate amounts of amino acids to be able to support its natural physiology. Those structures I talked about, they turn over. Red blood cells have a relatively short lifespan, so we are constantly making more red blood cells. We cannibalize the fragments of a dying red blood cell to reconstitute it into a new red blood cell, but we also sometimes need additional amino acids. We are constantly making hormones in our body. I mentioned insulin as an example, right? So every time we eat and we produce insulin, we need amino acids to manufacture that, because insulin gets broken down probably within 1 to 2 hours after it's being released, right? And if we're going to eat another meal, we're going to need to remanufacture more insulin. So that daily intake of protein, our dietary protein, is intended to support our physiology. And so we have a recommendation as to how much we should be eating. So on a daily basis, the current recommended dietary allowance is 0.8 grams of protein for every kilogram of body weight that you have, or 0.36 grams for every pound. So if you were to try and quantify that, all you'd need is your body weight, and you multiply by one of those factorials, and you'd get a target for how much protein you should be eating on a daily basis. Now, as I mentioned, this amount of protein supports your physiology. And it's conceptualized that this is the amount of protein needed to support most of the population. Right? They usually talk about 97 to 98% of the population, because we cannot guarantee everyone. But we also know that athletic individuals, people who are training and exercising on a regular basis, do need more protein. Because not only do we feed protein into the energy systems, if the nature of your training is resistance training, where you have an objective to build muscle mass to get bigger and stronger, well, you're going to need protein to support that growth of muscle tissue. That is protein that falls outside of the RDA. So generally, athletic individuals, people who are active, will need more than the RDA. Now, fortunately for most Americans, we don't have a protein deficiency issue. It's estimated that the average American eats more than the RDA, both men and women. But if you're an athlete, you probably want to be a little bit more strategic in terms of quantifying exactly how much. And we have guidelines for athletic populations that we will discuss in a later chapter in sports nutrition. So outside of our dietary protein, where else do we get our protein from? Well, we have two other remaining reservoirs. One is our living tissue, predominantly muscle tissue. Muscle tissue, which represents 30 to 35% of a woman's body weight, maybe 40 to 45% of a man's body weight, is a vast source of protein. And it represents 99% of all our usable protein in the body. So worst case scenario, if we have to cannibalize muscle protein. Why? Because either you're not eating adequate amounts of protein to support our physiology, or you're not getting enough calories generally to support the energy needs of the body, then we may have to cannibalize living tissue. Now, we may go to amino acid pools first. So what do we have? Well, within every cell and within our bloodstream, we have these small little amino acid pools. Call them pantries, if you will. So every time we eat, what we do is we first replenish those pools, because when we need amino acids for our physiology, that's where we go look first. So that needs to be replenished, and if that's not, unfortunately, we'll go after our living tissue. So the idea of eating on a daily basis is constantly replenishing these amino acid pools. But unfortunately, these amino acid pools are small. You know, when you think of your entire body weight, it may only represent 6 to 7 ounces, which is in the range of about 200 grams. Seems like a lot of protein, but when you consider how much you weigh, all right, it's a relatively small amount. So what is absolutely important to do is to make sure that you're getting adequate protein in your diet. Now, in some parts of the world where they have protein deficiencies, and in the US, where we generally see more of this with, outside of impoverished people, we see it more with older adults who may not be getting enough protein, it is pretty easy to get to that RDA number. And so what you see in the table here is just the amount of protein that we find in a lot of the common foods that we eat. So if you had a goal, right, to get to the RDA, so you calculated your RDA, and let's say hypothetically your RDA was 65 grams. Here's a listing of certain foods that you could kind of incorporate into your day. And I would advocate for an assortment of proteins so that we get more than just protein, but we're getting a lot of other valuable nutrients. And given that assortment of different proteins that you can choose from, you should be able to get to your total for the day. It's not that difficult. And what's also encouraged is not just to do it all in one lump sum. The best way to actually introduce protein into your body is to kind of distribute it consistently throughout the day. Now, not all proteins are the same. You know, we always talk about some proteins are a better source of amino acids than others. Essentially, every food that we eat has, for the most part, all the essential amino acids. But we can also, with a little bit more of a deeper dive into the different foods that we eat, we can also distinguish, although these proteins may have all the essential amino acids, some are still better than others. What do we mean by that? Well, what we are implying here is that when we look at what we need in the essential amino acids to support life, let's call it 9 essential amino acids. We vary from adults, between the adults and children. Those essential amino acids are not all needed in the same quantities. Certain amino acids are needed in larger quantities than others. And so when we're talking about essential amino acids, it's not enough to say, well, you're getting all the essential amino acids. We're really interested in, are we getting sufficient quantities of each of those essential amino acids? And when we look at what the human body needs, there is only one source of protein of all the foods we eat that is considered to be the whole or complete protein, and that is the entire egg, because an egg can support life. So when we look at proteins and we say, what is the most complete protein out there? There's only one protein that we can refer to, and that is the whole egg. Every other source of protein has some limitation in one or more essential amino acids. That doesn't necessarily mean that that amino acid is absent. It just means it isn't present in the ratios that we need to support life, much like the whole egg has. So for example, if we look at milk, milk has a limited amount of methionine in it. So it's not that it's devoid of methionine, an essential amino acid, it just means that it is low relative to the other essential amino acids that are in that protein source. And we can see it kind of going all the way through every other food source. Now, another thing to look at is when I look at the list of proteins on the left-hand side versus the right-hand side, there's something else that can be said too. This is not an exact scientific table, but the general consensus here is on the left you see more animal-based proteins, whereas on the right you see more vegetable-based proteins. And what we have discovered is that we tend to not only absorb, but we tend to see better amino acid profiles in animal-based proteins than we do in vegetable-based proteins. And so this poses a problem or a challenge for true vegans. There's some recommendations that true vegans might need to eat more protein than the RDA just to ensure that they're getting the adequate amounts of protein absorbed into the body. Because the reality is we absorb animal-based proteins more efficiently than we do vegetable-based proteins. Now, there are some exceptions to the rule. For example, pea isolates, some soy, and maybe even oats are absorbed pretty well. But other ones, like we find in cereals and grains and vegetables, we don't absorb them very well. So when I mentioned earlier that we should be looking at an assortment of proteins, it's for this very reason. Because much like when you are, looking at the ingredients to make, say, a cake, you've got to have the right quantities of each of your raw ingredients in order to bake your cake. Now, if I'm trying to build muscle mass or build some sort of structure in my body, I may have a set of instructions, a list of ingredients, so to speak. And I might need to have the appropriate quantities of different essential amino acids. Now, if my diet is consistently focused on one protein source, let's call it poultry, where methionine is something that is limited, I might be limited in how much tissue or compounds I can manufacture because of the fact that I don't have adequate amounts of methionine. So complementing proteins is something that we obviously recommend to vegans, but we also recommend it to everyone to make sure that we're getting the full array of all our essential amino acids that we need to support our physiology and to support, ideally, muscle protein synthesis. One last thing I want to talk about here is this idea of gluten. So gluten is a type of protein that we find in certain types of vegetable-based proteins. Now, in the chapter, I provide a list of what are typical vegetable-based protein sources that have gluten and those that don't. Because sometimes we develop some issues around gluten. Now, what you see in the table here is 3 different types of conditions. We have what's called a wheat allergy. Wheat is notorious for having gluten. We have what's called NCGS, which is basically a non-specific kind of reaction or sensitivity that you have to gluten. And then we have a diagnosable disease called celiac disease. Now, what gluten is, it's a combination of 2 different protein structures that kind of give this kind of gooey, kind of tacky sort of physical property to certain vegetable sources, which explains why bread is so kind of doughy, because bread derived from, say, wheat has a lot of this gluten in it. Now, some people, usually children, not so much adults, have a legitimate wheat allergy. Fortunately, a lot of children grow out of this. And if they were to eat anything that was related to wheat, so a product manufactured from wheat that had gluten in it, they might develop some of these allergic reactions. But fortunately, as I said, that's limited more to children rather than adults. When we talk about adults, we kind of focus on these 2. All right, this NCGS, which is really a condition, not a disease. In other words, there's no way to diagnose this. It's just simply something that is driven out of symptomology. So based on the symptoms that you experience, you might have some sensitivity to gluten. And when you look at the sheer sales of gluten-free products in the market today, right, there is just a mass of people who believe they have gluten sensitivities because when they eat, they experience some of these symptoms. they feel bloated, they feel some abdominal discomfort, they might even experience constipation or diarrhea. So automatically what they believe is that they have this condition. So what they do is they avoid gluten products. Now, can you eat have a healthy diet without gluten? Of course you can. There are lots of gluten-free vegetable sources of protein out there. But for a lot of people, it's unnecessary because they are misdiagnosing themselves, thinking that the bloating and the discomfort that they're experiencing, or the constipation and diarrhea, is all attributed to gluten. Well, it may be. It's not to say it couldn't be. So the smartest thing to do is to remove gluten out of your diet for a period of time and see how you feel. If you notice remarkable differences, then maybe you do legitimately have some sensitivity to it because you've resolved that symptomology you have. And if you don't, well, then obviously it means it's something else. There are other proteins that we could be sensitive to, or other compounds in our diet that we could be sensitive to. And then what some people tend to do is, once they've identified, yes, there are certain foods or gluten products that I'm sensitive to. Remember, not all gluten is the same. For example, oats have a type of protein that's very similar in structure to gluten, but it's not exactly gluten. So you might either remove other foods or introduce foods gradually back in to find your problematic ones. Because again, we may have different levels of sensitivity. Now, if you have celiac disease, this is an autoimmune disease that is basically triggered whenever we have the protein gluten in our intestinal tract. So what happens is the presence of gluten in our intestinal tract activates our immune response, and what it does, it actually ends up damaging the lining of our small intestine. And unfortunately, the lining of our small intestine looks like these fine microscopic hairs, right? We call them villi and microvilli, that generally increase the surface area so that we can maximize how much surface area we have to absorb nutrients into the body. And if you start damaging that lining, what you're doing is compromising your ability to absorb nutrients, and it will severely compromise your nutritional well-being. So people that have celiac disease, which is a disease that can be diagnosed, we have tests where we can diagnose celiac disease. Those individuals certainly need to stay away from gluten. But people that have NCGS, it might be something that's more psychological, psychosomatic, rather than something that's actually physically happening in their body. And as I mentioned, the best way to resolve this is to remove gluten temporarily out of your diet. Follow, a few weeks of a gluten-free diet, see how you feel legitimately, and then you might consider introducing certain gluten products slowly and gradually back into your diet.